everyone. This is the second installment of video for class for November 4th for the Science 121 at Luther College Fall 2020. And we're going to talk very briefly about main sequence evolution. We talked about pre-main sequence evolution in the first video, and we'll talk a little bit about post-main sequence evolution in the third video, but we're going to give that just a very broad overview and pick it up on Friday and walk back through it. But for main sequence evolution, there are really just two ideas that we want to make sure that we have. And one of these ideas we cover in lab this week pretty thoroughly. It's on the board in lab, and we've worked through it. But we're going to work through it again because it's that important. And that's the idea of trying to understand why high mass stars spend less time on the main sequence. And we're just going to go through the calculation we did in lab one more time and do it again here. And we're looking at slides 12 through 14 in your PowerPoint presentation that's out there. Particularly slides 13 and 14 is what we're going to walk through here right now. And what we see in lab, we're working with HR diagrams of open star clusters in lab, and we see pretty clear evidence in those HR diagrams that there's your zero-age main sequence, and we see pretty clear evidence that you got stars all along the main sequence, and then at some point they start to walk off and become giants up here. And so high mass stars are up here, and low mass stars are down here. And so the observational evidence that high mass stars leave the main sequence first is pretty clear. They walk away, and we can see other star clusters that are down here. We use star clusters again because they're just fantastic laboratories for studying this, because all of those stars were born at the same time out of the same cloud of gas, have the same chemical composition. We went through this in the lab introduction video, so we don't need to go through this too much. But to say some of these are way down here, and some of these are almost completely full up there. You might see a little bit walking away right up at the very top. And so what we're doing is in lab this week is we're measuring the ages of clusters by this turnoff point, how far stars have worked down the main sequence, to say, what mass of star has left the main sequence. Now, we should point out that there are often in these rich clusters, there are a few stars that dot past here, that exist past here, and we call those blue stragglers. And blue stragglers are these stars that shouldn't exist because they should have moved off. They're too blue, they're too hot to still be fusing hydrogen into helium in their cores as main sequence stars. They should have joined these other stars over here. Pretty sure what's going on there is that you have two stars that are orbiting each other, and they manage to merge. So you have two stars that have spent most of their lifetimes as lower mass stars, and they become one higher mass star. So they look like a higher mass star here, and they're hotter and more luminous than what should still exist, but they haven't spent most of their life as a high mass star. They spent most of their lives as lower mass stars, and so they haven't evolved as much as we would have expected. So the blue stragglers are interesting. You can see that. Poke around and look at some of the HR diagrams. You can see that. Certainly the HR diagram on slide 13 of the globular cluster right there. You see the blue stragglers that are out there. And it's interesting for us here at Luther. We've been shooting images of the same patch of sky for a very long time, getting close to 20 years now, and watching how the stars have evolved there. And that patch of sky includes an open star cluster, M23 in Sagittarius. And that open star cluster has a handful, maybe up to 5, eclipsing binary stars that are very short period. So eclipsing binary stars that have periods of less than a day. So these stars are orbiting around each other, basically touching, right? I mean, they're right on top of each other to complete an orbit in less than a day. And so, or 2 days or something like that for some of them. One of them is 9 days. But they're still very short. And so they're very short period. And so you see that story of these stars that are right on top of each other, about to merge into a single star and do this. So we're studying stars here at Luther that are on the verge of becoming eventually blue stragglers. They won't be blue stragglers immediately. They'll just still be on the main sequence. They'll just move up to a hotter spot on the main sequence up here. But then the main sequence is going to eat away and look like this and move down here, and they'll still be sitting there because they haven't been a high mass star as long. So anyway, we see that in process going on. We're studying some of those stars here. But what we want to think about now is why high mass stars leave the main sequence first, given all this observational evidence that they do. And so we looked at this in lab. We're going to look at it again. And one way to think about this is to say that we saw in class on Monday that, roughly speaking, all of this is rough. If you were, if you wanted, we'll talk about this more. There are ways that you could make this much more sophisticated and do a much better job. But we saw in class on Monday that the luminosity on the main sequence was proportional, roughly speaking, to the mass of the star to the 3.5 power. Okay, so you stick it in the mass, and it tells you, a 5 solar mass star is 5 to the 3.5 times more luminous than the sun. And so that's the way that we're doing this scaling like we did in the previous video. Now we just keep doing this kind of scaling to get a sense of why the universe looks like it does. We have to do this kind of scaling and to say, the universe looks this way, and it makes sense that the universe looks this way, and this is why. Now we're going to make the argument. So luminosity is equal to the rate at which energy is being used, which is the energy usage per time. That's a rate. Okay? So the energy usage per time. If we turn this energy here to the total energy, to say the luminosity is the energy usage per time, if that's now the total energy that's available to the star, and we divide then by the total lifetime of the star. So the main sequence lifetime, how long a star can be on the main sequence fusing hydrogen into helium. So the main sequence lifetime of the star down here, so that's that. If you look at the total energy, you've burned all the energy, then the total time that's elapsed is the main sequence lifetime. That's what we're talking about here. But the luminosity is still proportional to mass to the 3.5. So you have that going on. But we can ask the question then, or make the claim, that the total energy that's available to the star is going to be proportional to the mass. Now this isn't true exactly, and this is what I started to talk about earlier. With all of these, we're just making approximations to all of this. If you want to go to graduate school and you want to model stars, you're going to have to do a better job than this. If you want to help us understand stars and stellar evolution better, you're going to have to do a much better job of modeling what's going on here. But if you just want a broad overview of what happens as stars evolve, then what we're doing is great, and that's why we're doing it this way. But if the total energy available is proportional to the mass, that makes sense, right? If you've got a star that's, how you're getting energy is fusing 4 hydrogens into helium, and you've got a star that's twice as massive, it's got twice as much hydrogen to burn into helium. Now, the way that fails is to say the hydrogen into helium conversion is only happening in a little tiny spot in the core. Okay, so what fraction of the star is hot enough to burn hydrogen, to fuse hydrogen into helium? It might vary as the mass goes up. So as the mass changes, you might not have exactly the same fraction that's fusing hydrogen into helium. And there's another aspect that's going on too. As we looked at the model of the sun on Monday, often stars have a convective zone where they're churning material around. So material from up here is being churned down in here. And it is possible to churn material down into hydrogen, down into the core, and give it more hydrogen to burn. And so it is possible that you could have a different fractional size of the core. The core could be a smaller or larger fraction of the total mass of the star, but it's also possible you can feed that core more hydrogen by convecting material down in there. And the stars that do that, not all stars are equally good at doing that. Lower mass stars are better at convecting material down. And so again, this is a very rough approximation to say that the total energy is proportional to the mass of the star, but it's an okay approximation. It gets us where we want to go to see what's going on, to say, okay, if this is proportional to the mass, let's solve this. Let's move the main sequence lifetime up over here and put the mass down here, and then we're going to get something that says the main sequence lifetime. All we've done is done a swippy swapping. We move this up here, we move this down here, and that says it's going to be proportional to mass over mass to the 3.5, or 1 over mass to the 2.5. So again, mass is in the bottom, And if mass is in the bottom, then that means higher mass stars are going to have a smaller number over here. And we see that it's actually not linear. It's not even as the square. It goes as faster than the square of the mass. And so you can see this as 1 over mass to the 2.5. And it tells us that high mass stars should not stay on the main sequence as long as lower mass stars. Now let's do the same check that we did with the pre-main sequence. Let's put the numbers in for a 5 solar mass star and a half solar mass star. For a 5 star, 5 times as massive as the sun. My 5 didn't go well because I was holding chalk. 5 times as massive as the sun. That star would have a main sequence lifetime. 5 to the 2.5 power is equal to, so 5 x to the y 2.5, that's just what we did last time, equal to 55. And so 56. So roughly speaking, that's 56. This is again very rough, 50 to 60 or even 50 to 70 or something like that is the range. But let's just take the 56 that it is and say it's 56 times shorter than the life of the sun. The main sequence lifetime of the sun we're going to take to be 10 billion years. So if you've got 10 billion years for the sun, that's 10 to the 10th years that it spends on the main sequence, 10 gigayears. And so if we take 10 to the 10 divided by 66, so 1 exponential 10 divided by 56 gives us 1.8 times, let's say 2 times 10 to the 8th. So 200 million years is roughly is what this is. So we go from 10 billion years for the sun. The sun's around for 10 billion years. The 5 solar mass star is only around for about 200 million years. Now there's a table of these numbers in your book you can look up and compare this to see how our crude approximation compares to the lifetimes that are more that are calculated more seriously. But for us, we have the 5 solar mass star, we just said, is going to live 200 million years roughly. We got 220, but roughly speaking, 200 million years. 1 solar mass is going to be 10 billion years. And let's do the half solar mass like we did for the pre-main sequence evolution that we worked on and stick that in. And so we've got 0.5 x to the y 2.5 is going to be, let's do it the other way. Let's just do a 2 x to the y 2.5 is about 5.5. Okay, 5.6 we get right there. And so 50 to 60 billion years, 5.5 times that. Let's just call it 50. We call it 55 billion years, that's fine. 55 billion years here. And so now, we really see a huge difference here too, like we saw. These stars were made. There were over 200 of these stars made for every one of these stars, and these stars live so much longer. Universe is about 13.7 billion years old. That means every single one of these stars that's ever been made is still around. It hasn't evolved off the main sequence. If it's 13.7 billion years old, most of these stars that have ever been made are gone. We've gone through generation after generation after generation after generation of these 5 solar mass stars. The solar mass stars are there, they're gone, and they're gone. Every one of these stars that's ever been made is still there. So we made over 200 stars, half solar mass stars for every 5 solar mass star. Every one of these stars is there. Almost every one of these stars has evolved away. So you go outside, you look, there's 2 reasons you see a lot more half solar mass stars than you do 5 solar mass stars. One is they live a lot longer, and the other is they're much easier to make. You put those 2 things together, and you get a whole bunch of these stars for these stars, and the sun's someplace in the middle. Now 5 is not the upper limit by any stretch. You could have 10, you could have a 20 solar mass star, but those are rare stars you start to see from these 2 things that are going on. To say if you want a 15 solar mass star, a big OB giant star, way up high on the main sequence, those things, they just don't live any time at all. They're really hard to make, and they don't live any time at all. And so you see one of those, that's a special thing to be able to see that. So this is the lifetime on the main sequence. This calculation is what's laid out in slide 14 in your PowerPoint presentation, and we've talked through it here. Hopefully it's pretty clear. If you have any questions, you always contact me, and we can try to answer some of those questions. The last thing we want to talk about with main sequence evolution is the idea that stars, which we often say, you've heard me say it, and it's not quite true, but you've heard me say probably that a star, depending on what its mass is, that determines where it falls on the main sequence, and it stays there on the main sequence. It doesn't move up and down the main sequence, and that's generally true, but it's not exactly true. Because it moves, it changes luminosity, it changes temperature, it just does so in a way that's very, very small relative to how much it moves once it's get at pre-main sequences, it's falling onto the main sequence, and post-main sequences, it moves off the main sequence. Those are very dramatic changes in temperature and luminosity. On the main sequence, they're much, much smaller, but they're very noticeable. And so if you're living around a main sequence star and you stay there for several billion years, if you're around a solar type main sequence star, as we are, over several billion years, you will see changes. It's just significant changes, but they're just not like the dramatic changes that are going to happen on much shorter time scales, pre-main sequence and post-main sequence. So we're just going to basically write down the ideal gas law again, right? And we say this is nRT, the pressure. If we take the volume and divide it out, and we call that the number of moles or the number of particles. If we put K in there, this becomes a small n, which is the number per volume of particles. Number of moles per volume if we're using this R, number of particles if we're using the K. We don't really care. That's just the density of particles, number per volume. And what's happening in main sequence stars in the core is that 4 hydrogens are becoming a helium. So you're taking 4 particles and turning it into 1 particle. And as you take 4 particles and turn it into 1 particle, this volume density has to be going down, has to be dropping over time as we're converting the hydrogen into helium. And so as the number of particles in the core drops, you got to keep the pressure up. You got to keep the pressure up to keep pushing against the gravitational collapse. The temperature of the core has got to go up. And as the temperature of the core goes up, the rate of nuclear fusion goes up as well. And so you're going to get hotter in the core. It's going to make it hotter on the surface. It's a little bit tricky to calculate how much more luminous it might actually make it because the volume of the core is going to go down. That's the way you get the temperature to go up. You know this by now, is you have to collapse, right? You have to fall inward under the influence of gravity, and the temperature is going to go up. So you have a smaller volume there, perhaps, but you have a higher temperature. And remember that it's on the pp chain, the temperature dependence was about T to the 4th. So a slightly higher temperature gives you significantly more nuclear reactions going on. And so this suggests that stars do become hotter on the main sequence as they age. And so they a star like the sun, I don't remember the exact number, but its temperature is going to go up significantly over the course of its main sequence lifetime. If it's 5770 Kelvin right now, I wouldn't be surprised for the temperature to go up, for the luminosity to go up. The temperature to go up, I'm not sure why. The trick is this: as the core collapses, it can push the outer layer of the star out, so the surface might not heat up as much as the surface might actually go down, as we're going to see with post-main sequence evolution in a moment. As it expands out, the surface can actually cool, even though the core is hotter. So the real trick is the luminosity might go up here, and the luminosity of the sun could go up by as much as 1.5 or 2 over the course of its lifetime if you get to be a significantly brighter star than it is right now. I'd have to check those numbers out, so don't hold me to those numbers, but to know that this is what's going on the main sequence. So now, once we fused all the hydrogen into helium in the core, we have to move off the main sequence and become a post-main sequence star. We're going to talk about that evolution in the next video. We'll see you in the next video, everybody.